online? Okay, got it. Yes. Yeah, on Zoom they can hear. Yeah. All right, perfect. Thank you. Yeah, thank you very much to allow me to give the last talk of the day and of the conference. I at this point realized this presentation is what stands between dinner. All right, yeah, I stand between you and dinner. Yeah, and it's actually really nice to be back at the IRM. I visited once as a PhD student in 2015 when I was working on tectonics of Anatolia and to understand a little bit more of one of the methods that I was using, which was paleomagnetism, out of other methods as well, to basically learn the basics of paleomagnetism in the School of Rock here at the IRM. That was great, and so it's really nice to be back. I will be talking today about embracing uncertainty and noise in paleomagnetic data, and previous speakers have already outlined a lot of the underlying basics and a lot of the statistics. So that's really good, because I am worried that my talk is too long. All right, so just a bit on the background and the tectonics toolbox that I developed during my PhD. So my PhD was on reconstructing the tectonic evolution of Anatolia, and specifically the Neo-Tethys Ocean from the geologic record, using the rock record to reconstruct that oceanic lithosphere that is no longer at the surface. And to do that, did a lot of field work, needed age constraints, so collaborated with a group of people doing radiometric dating of magmatic and metamorphic rocks, but also getting constraints from sediments through biostratigraphy. And then paleomagnetism came along, and I mainly used it as I was working on Turkey for vertical axis rotation. So for those of you familiar with the geology of Turkey, a lot of things are quite rotated. And yeah, that was kind of my introduction to paleomagnetism, and I kind of left it at that for a while, until recently I got interested in marine magnetic anomalies, where through COVID I spent a lot of time at sea. And one of the byproducts of that was then this interest in being able to collect magnetic data from, in this case, from the Coral Sea. So this kind of data is useful because it informs kinematic reconstructions. I was working more on a regional scale, so detailed plate kinematic reconstructions of the Neo-Tethyan realm from the Cretaceous onwards. But then these kind of detailed regional reconstructions can be incorporated in global models, and they can be tested again against mantle structure. And this is very much an iterative process, and depending on which group you're in, you might be doing this from one side or the other. You might be doing it from a seismology slab side, or you might be doing it from a geology paleomag side. And they kind of complement each other. And paleomagnetism is really what I'm trying to show here is the only quantitative tool that we actually have to describe plate motions through time, especially when it comes to Cretaceous and older stratigraphy. So I'm going to present today two kind of case studies where the first one is going to be on the late Cretaceous, and specifically the late Cretaceous superchron. And then the other one will be the 60 million year, or the apparent-polar wander path since 60 million years for the North American continent. And as you see in this plot, going back in time, we actually have a world, like our world uncertainty, our constraints of what we know about plate reconstructions and the configuration of the plates changes progressively. And so this world uncertainty goes significantly up once we kind of pass that Cretaceous point. Let me just see. About that. Yeah. So, and the reason for this record also being lost with time is that we actually don't have oceanic lithosphere that is much older than 180 million years. There's a few exceptions to that, but in general, that's kind of the limit. And then we are left here with.
You have your charger.
It is plugged into the charger here. So I think. Okay. Yeah. So after that time, we basically rely on paleomagnetism, or before that time, paleomagnetism and geology and paleontology. So plate reconstructions in general have proven to be really important for understanding the many different Earth processes that take place on the surface, but also those have implications for processes deeper inside. And it's the only truly quantitative tool to determine these pre-Cretaceous plate motions. And the way that we summarize paleomagnetic data is we assemble it into apparent polar wander paths, which actually represent a time-dependent position of a plate relative to the Earth's spin axis or vice versa. And then we make these models, and some of the models now go back to 1 billion years. And what you see here is the time-dependent position of the plates based on underlying data, which we here don't see. So here we're actually blurring the image between data and models, and we're currently unable to really show uncertainties and where the data are actually sitting, where the quantitative data for these kind of reconstructions are sitting. And essentially this means that in a perfect world, well, it's perfect once you actually combine all the observations into a single best fit model. And the result of that is that at the end, the uncertainty in the end result is actually uncertain. Yeah, so this is a recent review paper by Seaton et al. For those not familiar with plate reconstructions or just in general interest in it, I think it's a really great summary, especially for fields like geobiology, paleoceanography, and all these related fields to our discipline that are using the plate reconstructions to then make inferences about, for example, climate change in the past, but also in the future. So I think that's really important to outline the underlying data, and that's exactly what this paper has done. And here what I'm showing is a figure from this paper where you see at the top the maximum age of the oceanic lithosphere being round about like Jurassic. So that's timescale is different than the other plots. And what you see is that we have pretty much no data, or barely, yeah, no data in the Cretaceous normal superchron. I will add two data points to that further in the presentation, but then nothing from 180 onwards. And then we rely purely on data from the continents. And you see that even, I think it's when I see you see, and then it just dots. And then when we go further back in time, you see, I'm not going to see you see. So then we can see that there is underlying data, but actually, even when we have data, there is, of course, discussion on the position of certain continents in time. So that this is not able to capture that. It's just showing where the data is coming from. And then, of course, we have geologic events, which then again are, based on interpretation in a way. But this is the underlying data of the plate reconstruction or generally of plate reconstructions. So actually this paper has then concluded, or one of the concluding paragraphs actually starts with a heading that says all models are wrong. And this is written for people, for a general audience as well, or is very beneficial for a general audience that uses these plate reconstructions, as I said, to infer paleoceanography or paleobiology. So they caution us to use, when we use reconstructions as data, it is crucial to keep in mind the underlying assumptions of different reconstructions and the distinction between those aspects of global models that are well constrained by data and those which are interpolated or extrapolated. And also, I should mention, there's a real difference between regional models, the resolution, and the global models. And then additionally, we have this gap in time and progressively losing resolution through time as well. So when we look at a global apparent polar wander path, you actually see or what they portray is so motion through time relative to the spin axis, but also what we see here quite clearly is that we have these cusps where plate motion changes quite significantly and maybe quite rapidly. But is this really the case? Or is this an artifact of how we treat our data? That is really, that's a big question. But we also see cusps in the geologic record. If we look at the modern ocean floor, you can see places here highlighted in pink in Cara Matthews' work on a compilation that concludes that there was a late Cretaceous plate reorganization around about 105 million years. What she shows here is that these the marine fabric can have bends that we might assign to plate motion changes as well. So this kind of was a curiosity at the end of my PhD work, where my job was to reconstruct this ocean of the Neotethys that no longer is at the surface from the geologic record of this region, and so the Anatolian region. And I came across this paper from Roy Granot here on the left, who had discovered intensity variations in paleomagnetic data, or in marine magnetic data, towing a deep tow magnetometer. And they had crossed the central Atlantic across this black zone here. And what they've observed is that we have intensity variations in the intensity of the magnetic field that they observed on both sides of the mid-ocean ridge. And that has then led them to conclude this might be the primary signal that we are observing in the Cretaceous normal superchron, which could be also tested elsewhere. The age correlation, so there's two of them. So two intensity variations termed Q2 and Q1. One is at 108 million years and the other one is at 92 million years. And they're not reversals, they're just like changes in their intensity variations. And the ages of these are assigned using, so indirectly assigned using the SDP cores that have recovered rocks close to those magnetic peaks. So by using this data that was published by Roy Granot and his colleagues, I was able to, we were able to actually constrain two additional stage poles in our plate reconstruction, so regional reconstruction of the African plate relative to the Eurasian plate. So this Neotethys ocean that had to be kind of reconstructed using this loop through the central Atlantic. So because we're using plate circuits, we can use indirect loops to portray the motion of Africa relative to Eurasia and also North America. So once we've implemented Q1 and Q2 shown here, and gone missing there, but like, yeah, so you see that originally models were basically sweeping across this Cretaceous normal superchron without these two additional stage poles. And once we are able to implement these stage poles, we actually can show that there is an acceleration, so the convergence rate jumps up. But it would, of course, be nice to have more stage poles in the Cretaceous normal superchron. But this is what we have. So that then led to the formulation of the concept of a plate tectonic chain reaction. The reason being is that I and the team actually had worked on a lot of different parts of this Neothethian system, and we were able to constrain tectonic events from the geologic record quite well with quite high resolution using geochronometers. So we could date subduction initiation at 105 million years. And this is like a recurring age. This 105 million years seems to be coming up for the Neotethys. And that then kind of sparked my interest in these global plate reorganizations. So what we then did was to constrain these two stage poles and be able to actually sequence the tectonic events to kind of find an order with these additional stage poles. So what happens is at 105 million years, the second subduction zone initiates within the within the Neotethys as an intraoceanic subduction zone. And we think actually that the African plate motion, the pull off that second subduction zone, because we have an additional subduction zone that already is active at that time, that actually might have caused the rotation of the African plate and the extreme speed up of it. So that's what we then kind of put in this cartoon, how this worked with that. We had this far field forcing at 105, subduction initiates, the second subduction zone initiates, we have plate acceleration, rotation, and then that has trickle down effects along the plate tectonic chain reaction. But to be able to establish and actually test this concept, we really need to, we require better temporal control, but also spatial control. And this brings me actually to higher resolution apparent polar wonder paths from paleomagnetic data, which is a paper that was mentioned today already. As Yiming mentioned, it's been published just 2 days ago, or a day ago. So it was led by Leandro Gajo and Matt Doymeyer at SEED in Oslo, and a group of us got together, some in person, some online, this was still in the pandemic, and compiled apparent polar wonder paths from VGPs for the North American continent. So this was a great initiative, and as I will show you, I will encourage the community to do this for different continents, and all you need is 13 friends and a week somewhere in a cabin, and yeah, lock yourself in and just start compiling. And this is the associated paper. So during this workshop, we had a lot of questions, and there wasn't a set theme in the beginning other than frontiers in paleogeography and paleomagnetism. And these are kind of the questions that we then kind of settled on. So what are the real uncertainties in apparent polar wonder paths? What resolution can they reach? And what do they actually look like? Should they be really, I showed these cusps in one of the apparent polar wonder paths that I showed, are they really angular, or should they be more smooth? And I think that one is not settled, so. And what we then did is to start compiling data at site level, actually, to be able to get to these high resolution apparent polar wonder paths. And one challenge of dealing with paleomagnetic data that it's very hierarchical. So if we have different levels of data collection, and at each level, we introduce uncertainty. So uncertainty starts in the field when we take a rock, and some of the measurements might be a degree or two off. You combine that to site level that has associated uncertainties with it. Then you combine that into study level, depending on the age. And again, I should probably mention here also age uncertainties, which also add to that database, to that data set. And at each level, we have these uncertainties, but we're not propagating them through the hierarchy, which is a problem. So here in this plot at the bottom, courtesy of Andrew and David, we move from left to right, and at each step, we kind of lose that uncertainty, so we don't propagate it. Other shortcomings are, so we have this artificial hierarchical level. Yes, uncertainties are not propagated, but also we assume parametric distributions. And I will show you two examples of, two of many examples where this parametric distribution might not be the best way to describe the underlying data. And then, of course, inherently, because we're human, underlying data are variably processed. So there's very different criteria and not an agreed protocol, so to say. And this is already something that's in terms of the uncertainty propagation, David and Andrew had published some papers on. So again, here, incorporating where the field was and what it needed in terms of pushing the pushing the frontiers in paleomagnetism and paleogeography through an early career initiative. We then decided, okay, this was really something we wanted to know more about, and that's what we've done. So because Yiming and Bram already have spoken about it quite a bit, I'll just quickly show this plot. But what is actually one of the things that we did to get rid of that artificial hierarchical level is to use VGPs or to construct VGPs instead of the conventionally used paleopoles. And that takes out that, that hierarchical level. And if you want to know more about that, there is Bram's paper that he presented on earlier today. Then in terms of the uncertainty propagation, maybe it's that I'm standing there. So in terms of the uncertainty propagation, it had already been pointed out that there is no clear approach to this problem. And all right, and that we actually are not really doing the data justice in the sense that we're actually losing some of the data that is really valuable, that is attached to those poles as uncertainties. And that at each level, if we're applying mean poles, that might not really represent the data well, and that we might be thinking of other approaches. And again, this had already been pointed out by Heslop and Roberts in 2020 and 2016. The challenge here is that we can do this either top down or bottom up, but there is a mathematical complication in the middle where these two things meet. And that has to do with the transformation from directional data. So from a direction space to a pole space, there's a transformation that is needed, which goes above my mathematical background. But I think David and others, and maybe Nick, would be really interested in discussing that. And this has been done already actually by Hansma and Toger. They had already outlined that there is a problem with the lack of propagation of errors. And they've actually highlighted that on a data set on northeastern Australia, where they show that they can actually, through bootstrapping, propagate these errors in a more fair way to the data. So we can propagate these uncertainties numerically from any hierarchical level. So we can start at sample level. The problem often with the sample level is you can't get to the original data. I've tried that for the small data set to ask the original authors for the sample level data, but it's very, very tricky to get to sample level data. So we started at site level, and we also did this bootstrapping for the ages as well. So also age uncertainties are propagated in this data set. So then the third shortcoming was that we said, okay, yeah, usually traditionally we assume parametric distributions, but as shown in these two examples, yeah, paleomagnetic data or nature doesn't always behave according to this Fisherian distribution, and sometimes data can be quite skewed. And by bootstrapping instead of that, we might be able to avoid these assumptions that actually skew the data. And this is another one that I mentioned here, that the underlying data are variably processed, so kind of human error. Yeah, because there's different approaches on the minimum amount of samples. Also, it depends on whether you're sampling volcanics or sediments. So different approaches, the maximum radius of alpha 95, and also the maximum angle away from the mean. And again, through this approach, we are able to resample, and we can eliminate and combine data sets that are usually published separately based on their, for example, age. We can combine them and resample them. So in a way, that takes us away from comparing apples from oranges. So we are able to resample, put it back, and resample again. So we can this way we can retroactively apply the same filters to all data sets that we have the original site level data to, or any level, but yeah, you can always move up in the hierarchy. So this then led to this VGP compilation of North America for the Cenozoic, roughly 2,000 sites from about 40 studies. And again, age and uncertainty, age and their uncertainties were assigned. The stratigraphic ordering of samples was logged where known, because sometimes you can only derive that actually from figures in the original papers. And then we also, we recorded all that metadata. Originally rejected data by the authors was incorporated in that it was noted and also noted why it was dismissed. And repeated instances of the same site were also logged. And all this data is now loaded to the MAGIC database. And this is what it looks like. So this is the, this is the data compilation for the past 60 million years for North America, noting that there seems to be, a sampling gap between 10 and 20 million years, which is, I think, interesting. But otherwise, we have a pretty large spread in terms of ages and locations. And just to run through this stepwise process, this is what's been done to compile all these data. So we had the site level data that we tabulated, and then for each site mean in the data set, we did this resampling using Monte Carlo simulations to generate a new datum that we could then replot or like recalculate with other data. So we kind of separated it from its original study and combined it also with the directional and age uncertainties. These were then used to build VGPs. And then these were then, the VGPs then were used to, in the fourth step, compute a weighted moving average of the VGPs for a certain time window with a moving average. Yeah, and this approach allowed us to overcome the shortcomings that I mentioned in the beginning. And again, this kind of approach can be deployed to also other data sets like age data sets and any hierarchical data sets. But hopefully it'll be useful for the community to compile other data sets. And this is essentially what now the new improved apparent polar wander path for North America looks like. And actually it can be decomposed in its different components. And I'm just showing here the latitude, the change in latitude, longitude, but also you can see again here the time gap between 10 and 20 million years. So you can look at the data from different perspectives in a way and get a fuller picture of uncertainties and other associated data, metadata that we conventionally actually do not look at or do not include in our data sets. And the same approach, we're deploying the same approach to put Australia back on the map. So Eastern Australia doesn't seem to be fitting, anything to the east of the Tasman line doesn't seem to be fitting the apparent polar wander path of East Gondwana relative to West Gondwana. And actually, we're hoping that with this approach, we can contribute to the discussion on the controversy why these data might not be fitting. As you see here, this is a compilation that Matt Doymeyer did back in 2012. And he shows here quite clearly that the apparent polar wander path from Eastern Australia, based on these poles that are shown in red, and then poles also from Pakistan and India for roughly the same time frame, do not fit the Permo-Triassic poles from Eastern Gondwana. So this is work in progress. Again, about 1,500 site level records from about 30 studies. I should mention there's a pretty good spread of ages, but actually in terms of, because we heard it before, Australia is really big. Spatially, there is really big gaps. Again, same protocol. I'm not going to repeat it. And eventually it will be uploaded into the MAGIC database. So very much so work in progress. I'm actually on the 5th iteration of tabulating the data, and because the approach has changed through time. So I had been in the 2nd iteration, I think, and then the seed group got together during this conference, and we changed it again. And then, yeah, subsequently a subgroup got together and changed it again. So it's been very much work in progress, and yeah, hoping to finish this compilation before it moves on. Yeah, and this is just a kind of summary, really, to mind the gaps and the noise in paleomagnetic data, because there might be really valuable information in magnetic noise, as well as in uncertainties that we conventionally drop. And the take-home message here is that based on especially the North American study on the Cenozoic, that even in the presence of substantial noise, polar wandering can be assessed with really, really high resolution, both temporally and spatially. And that actually leads me to conclude that not all who wander are lost.
Thank you, Dario. Are there any questions from the audience? Before I forget, I also noticed that there was one comment in the chat, and it's been there for a while, so I need to add it. Okay, question please.
Thanks. It's more of a facetious comment than a question. Not special. So with the statement that all models are wrong, but some are useful. Since we're talking about uncertainties and so on, I would counter that and say that all data is wrong as well.
Well, maybe it's
all
a bit.
So if you quote your data, without uncertainties, the probability that your data are correct is 0. Mathematically, you can show it. Yeah. The only way that you can get your data to have a probability higher than 0 of being correct is to quote uncertainties.
Yeah, and I think that's the challenge to, well, we now show that we can actually propagate the uncertainties for paleomagnetic data, age data, but how are we going to actually portray it in a digestible way for the audience? Because even, yeah, undergrad students, for example, they see these plate models and they say, well, why bother studying paleomagnetism? We seem to know everything, because the world is already kind of perfect, and that was the point of that slide. Yeah. So it would be interesting.
All data is wrong, but some is useful.
Some is useful.
Stuff is the stuff with uncertainty.
With uncertainties. Yeah. Thank you, David.
Need to work on your grammar, man.
Any other questions here?
Now there is a comment.
Now there is a comment. Maybe.
Okay, yeah, so the 10 to 20 million year data gap for the North American continent. Well, I think it's surprising. Like when I saw it just today, I kind of revisited the latest figures in the just published paper, and it kind of stood out again. And then I just went online and had a look, and it seems like Columbia River basalts is about that age. I assume that's one of the
there's a big documented rotation.
Yeah.
Yeah, so that's what's tricky about it. So anyway, where there's some of those, so Columbia River basalts, you think are sort of natural, but all those data has been collected that there is sort of rotation there. But a comment on top of this, which I think is a really sort of valuable thing that comes out of this approach, similar to sort of finding the gaps, is that you're visualizing the gaps, right? Like often it's been like, we don't need a paleopole at X age for X continent because we have more, right? But that's sort of at this hierarchical level where someone measured, 12 mafic dikes in Sweden that are 850 million years old, and now you've like solved it. We have everything we need for Baltica, we can move on. Whereas I think what you see here is there's just, you can actually see how many like sites, how many virtual geomagnetic poles underlie each part of the path, which you nicely illustrated. And so it both goes where you need more data, such as in that, but also you can sort of constructively build up more data sets by bringing more sites into the picture. Once we're sort of moving past that artificial hierarchical level, as you put it, of the study level summary pool. But I think in some ways, like things like that, like you can use this very much as like a call to action. Like someone could take a screenshot of that figure and write a proposal to develop a bunch of Miocene data in North America. Like there's places you can do it, right? So I think that's in terms of sort of us, that place really cool.
Thank you, Nick. And just to add to that, like I think one challenge or one way forward will be to have these data hackathons where you go and compile some paleomagnetic data and then assign the gaps and then justify paleomagnetic fieldwork for decades to come. Like I think that's really important because these gaps, I mean, the North American continent in terms of paleomagnetism is really sampled in a way. For example, in Australia, it's a lot patchier through time, probably also. Maybe size is not the, density of population. But I think that's probably going to keep us busy for a while to fill these gaps. And then revisiting old sites and compiling data from repositories, and also maybe working on the way we report data in a more fair and accessible, reproducible way that we can contribute to one database where all these uncertainties can be propagated from site level. Originally, I thought this would be possible from sample level, but I mean, it would be possible, but it's take a long time.
Yeah, thank you. It's really nice work. I just have a question about, it's more a philosophical question, but maybe useful. I think one of the reasons that the North American data set is maybe smaller than you might think is that there was a very conservative approach to the construction of the North American apparent polar wander path, recognizing laramide deformation, early phases and later phases of the construction of the Rocky Mountains could be inducing rotations, as well as then rotations, later rotations along the whole West Coast. So that's one part of it. I'm concerned about some of these global compilations that, and there's a certain justifiable approach there that one should be worried about these later events. It seems that sometimes when we go back into deeper time and constructing apparent polar wander paths, we don't worry about that. And then all of a sudden we start combining data from places that are actually separated from orogenic belts or some tectonic activity, and we call it one craton. So, one solution to this, of course, is to break things down and start using inclination-only data. If you have volcanic rocks, to parse out the various weaving we use to worry about these types of deformation anomalies. Has your group thought about that at all?
Inclination-only data, or just inclination in terms of just using sediments, sorry.
No, not using sediments. So for example, you could go to North America, you could go to rotated domains and use the inclination components from those studies.
Yeah, that would be one approach, and also correcting from vertical axis rotation work in Turkey. So that was based on sediments. But by sampling a lot, we still would be able to calculate all from that data because the data set was so big. But as you say, the rotation is a worry. So I'm not sure that it has been applied. It's something that has been discussed in the workshop. Or after the workshop, and I'm not entirely sure how much it would add. I'm not sure because I don't know how much data that there is actually. Because we don't show the underlying data usually. If that makes sense.
But yeah, I mean, I think that's motivated from a lot, sort of going back to his topic, sort of the summary, right, is actually thinking about how we can be doing these assessments, both not only of displacement, so like in the sort of India Eurasia problem, but also of vertical axis rotations. I think that's actually, and I guess that's sort of Brown's final point, and I'm interested to see his paper, right, in terms of trying to get to a apples to apples comparisons between what could be a displaced or interpreted to be rotated terrain and something that you're more confidently a stable on it. I think, for example, for the very Colorado plateau rotation point you brought up, that that sort of like there's pre-inclination shallowing in terms of those comparisons, right? And I think applying some of these methods in that context to address those very questions. Yeah, do that forward. But I think your point of doing times doing the inclination only, particularly where you're just worried about vertical axis rotation, I think is intriguing. And when you're in the sort of framework, you have more flexibility to do that.
And I'm also wondering if we would just use inclination data when we go further back in time, the constraints on how much vertical axis rotation there is that affects the destination. How do we know that it always just rotated in one way and not the other? I think that might become a problem going further back in time. Just the thought that yeah, I'm not sure whether that can be statistically, or whether the weighting of events that we have better constraints structurally could be just like portrayed in data sets like this.
I guess my point would be that you have this compilation, and this is an opportunity because it's really a question of site distribution. So inclination only data can be extremely useful if you have the site distribution, so you have the intersection of the inclination data to constrain a pole position.
Mm-hmm.
So it's going to be very much dependent on your sampling and just what's available. But I would suggest that you look out. There might be something interesting.
Thank you.
So I'm tremendously heartened by young seed. We talk a lot about, as far as I'm concerned, it's the conversation been going for 30 years about, oh, there's labs are closing and all of that. But I'm tremendously heartened by a group of young people deciding to embrace uncertainty and redo things. And I wonder if you could show us your final plot, because well, the final APWP, because what I expected when you embarked on this was that it would just be the same as the existing one, just with uncertainties blown through it. But actually, I think what you've shown is that it's quite different, is it not? Does this figure show it or not? No, right now.
It's a Cretaceous small supercompound. So this is the plot that I originally did not show. Do you want me to go to the one that I actually showed?
Leandro showed one in Vienna, which left my jaw on the floor, actually.
But this is the final apparent pole on the far right hand side.
Right, compared to, where's the original?
Towards the lake. Panel A, yeah. So that would be more like Torschvik et al. 2012 would.
So I think that's a really interesting outcome of all this, that when you propagate the uncertainties, you're getting a very different looking result.
Yeah. And what I'm now just in discussion for the past few days, because as I mentioned also, there has been different versions, of course, also of the papers with reading and things. And what you see is that on the far right, there's actually the path looks really smoothened in a way. It looks like it's got that very much unlike the other paths that I showed. And the question is, how real is that? And it has to do with the way this moving average has been calculated. So it's to do with that we're rating the mean that is in the middle of the window more than to the sides of the window. So I'm not sure whether that's something that's going to be changed or like, yeah, reiterated. So, but thank you for your compliments. I'll pick up for the team.
Yeah, and I can't wait to see this done for the whole timescale, right? It's a massive job, but I think more community efforts to do that, to propagate the uncertainties through the hierarchy are really critical for getting to a model that approximates reality better. Thank you.
Thank you.
Any other comments or questions? Yeah.
Hi, I will try to say a question. In my mind, I think that when we do paleomagnetic study, we have sampling error, we have the measurements, the adjustments of components and Fisher mean of directions, and then we do the average of VGPs and a paleomagnetic pole. And then when we put together paleomagnetic poles from single plate, I think a source of error can be some displacement that we cannot detect. So in my mind, I think a good distribution of paleomagnetic sites in a continent will be better than one place only being something. I know that if we, considering the number of VGPs from each paleomagnetic study is statistically fair, because you are putting together, putting together studies that has like 100 sites and the other with only 5 sites. Seems that not fair with the guy that did 100 VGPs. But I'm thinking about when we do this, we are not putting too much weight in one place. And in my mind, this is not good for defining paleomagnetic pole for continent. So what do you think about it?
Yeah, so thank you for that. So that relates to the, I guess, inherent bias that we have when we go do field work. But I think that's the roadmap. Like this is probably the most recent compilation on where we are actually ought to go. And of course, you could increase this in resolution and have like different parts of the different continents. But yeah, I think this is what these databases and data compilations will actually be really powerful in showing for paleomagnetic data. Maybe also like we heard from Emily that like there's databases for age data that way you can assess, like where you can download the data, and there's a bias in the age data as well, and very sample. So maybe by putting these different data sets together in one platform where we can assess where things are missing and then address that problem of the bias in where we sample, unless there's a geologic reason for it, there's not of a certain age and a certain region. But otherwise, I think this will be kind of the roadmap of where to go and in which times, like time frames. So in a way, maybe kind of deconvolute that world uncertainty that I showed for certain regions through time, like, yeah, make it more detailed in a way. And I think that's a really fair point that these kind of attempts will probably hopefully inform my reverse sample in the future. Yeah. So I'd be keen, I don't know much about North American geology, other than, you know, the compilation, but seeing something out between 10 and 20 million years, it seems kind of like pretty recent, and there's volcanism, so I always kind of assumed it should be pretty straightforward, but yeah, maybe reason to stay longer. Or to go to dinner.
This is very good. Thank you very much, Daria. Thank you very much, all the presenters, and I don't know if Max